How has what we call space evolved from an abstract idea to a place that humans passionately explore? And how has space become the arena for some $350 billion of annual economic activity? I'm Dan Baker, the director of the Laboratory for Atmospheric and Space Physics at the University of Colorado in Boulder. I want to talk to you about those questions today. Today we think about space, we have to consider the business of space. It's been quite a ride watching the economic model develop. Where will it go next? What awaits us in the business of outer space? For our ancestors, the concept of nothing, of a vacuum, was hard to fathom. Greek philosophers presumed that something must exist in space to hold the sun, the stars, the planets in the firmament. How could it be otherwise? Even into the late 19th and early 20th centuries, scientists believed that there needed to be a medium through which light from stars spread to Earth-based observers. Scientists of the day called this hypothetical medium the ether, and famous experiments like the Michelson-Morley experiments were carried out with exquisite precision to measure the ether and its effect on light transmission. But as Einstein famously showed, light travels at the same speed, c, in all vacuum frames of reference and in every conceivable direction. There is no ether. As scientists contemplated the nature of space itself, science fiction writers like Jules Verne and H.G. Wells fired people's imaginations by writing about humans traveling to the moon and to other planets. But this dream of human spaceflight also fired the imagination of scientists and engineers who became passionate advocates for rocketry. In Tsarist Russia, as early as the 1890s and 1900s, Konstantin Tsiolkovsky understood that rockets could propel huge objects into space. As a passionate teacher, he planted the seeds for later Soviet Union space exploration. During the 1920s in Germany, Hermann Oberth developed advanced ideas for liquid-fueled rockets. His ideas became the basis for German weapons like V-1 rockets and laid the visionary basis for deep space exploration. In the United States, Robert Goddard is widely viewed as having ushered in the space age. He developed liquid-fueled rockets, gyroscopes, steerable thrust systems, and he pioneered multi-stage vehicles, all largely without public funding. Goddard is truly the father of U.S. space exploration. From these early roots came ideas on how to employ rocket propulsion for weapons of war. The Vengeance 2 weapon, or V-2 rocket, was developed by Wernher von Braun in Germany during World War II. Late in the war, von Braun and many fellow German rocket scientists defected or were captured and came to the United States. The work of von Braun and his team led to the successful development of U.S. intercontinental ballistic missiles, or ICBMs, and led directly to the first U.S. scientific satellites. In the Soviet Union, Sergei Korolev was the mastermind behind the rapid development of Soviet ICBMs after World War II. He was also a shadowy figure, unknown by face or name in the West, and he was dubbed the chief designer, whose efforts launched the first satellites into space in 1957 and the first humans in 1961. Today we remember that the Cold War, spanning from 1945 to 1989, was a time of great tension and great competition between the Soviet Union and its eastern bloc of nations and the US and its western bloc. Huge numbers of nuclear weapons were fielded in ICBM nose cones, and the world was held in the grip of mutual assured destruction, or MAD. But the flame of science still burned brightly during the Cold War. Competition for the hearts and minds of the world's citizens led to the space race between the East and the West. The Soviet Union amazed the world on October 4th, 1957, by launching Sputnik, named for the Russian word meaning companion, into Earth orbit. Sputnik 1 was little more than a radio beacon, but it showed the sophistication of Soviet missiles and guidance systems. This frightened people around the world, often to the point of hysteria, since it was now possible for ICBMs to strike anywhere in the world in a very short amount of time. Sputnik 2 was launched just a little more than a month later, on November 7th, 1957. It was much larger and more advanced than Sputnik 1. On board were the dog Laika and radiation detection instruments provided by Professor Sergei Vernov. Sputnik 2 had its apogee over Australia, not over Russian territory, and the telemetry from the spacecraft was encoded. So the Australians recorded the satellite telemetry data and asked the Soviets for the code to decipher the data, but the Soviets refused. The Soviets, on the other hand, demanded the data recordings from the Australians, and the Australians refused. So the Vernov radiation belts faded into oblivion. It fell to James A. Van Allen, Wernher von Braun and William Pickering, pictured here, from the United States to make the first great discovery of the space age. They found that the Earth is shrouded in intense toroids, or belts, of high-energy particles. We now know them as the Van Allen belts. Sergei Korolev and his secret team of Russian rocketeers continued to amaze the world. In 1961, they launched the first human, Yuri Gagarin, into Earth orbit. The US was far behind and only launched its first suborbital flight a month after Gagarin. The first US human orbital flight was with John Glenn in February 1962, almost a year later. The remainder of the 1960s is characterized as the intensely competitive space race era. The US Apollo program saw the first landing of humans on the moon in July 1969. The Apollo astronauts Neil Armstrong, Buzz Aldrin fulfilled President John F. Kennedy's challenge to land a human on the moon and safely return to the Earth within the decade of the 1960s. The Apollo program continued with great success until 1972. Then both the politicians and the public began to lose interest in spaceflight. The quest to beat the Soviets was over, and the US had won the space race. During the 1970s, we saw the slow development of the space shuttle, and in 1981, the first shuttle flights occurred. The shuttle flew dozens of successful missions until the tragedy of the Challenger disaster in January 1986. 7 astronauts lost their lives in the Challenger disaster, and space shuttles were grounded for over 2 years until the resumption of flights in 1988. The loss of the Columbia mission in 2003 nearly caused the permanent demise of the US spaceflight program. The remaining space shuttle vehicles did fly missions to the International Space Station from July 2005 to July 2011, but no human ventured beyond low Earth orbit after the Apollo missions. In a very real sense, humans have been flying in circles since 1972, confined to our home planet. Although humans have been confined near Earth for over 40 years, robotic exploration and commercial space have thrived. Since 1972, the end of the Apollo program, missions have been sent outward to Jupiter, Saturn, Uranus, Neptune, Pluto, and beyond. Missions have been sent inward to Venus, Mercury, and to the outer layers of the sun. We have developed Earth satellites to sense all aspects of our home in space. Communication satellites, weather, reconnaissance, navigation, and countless other satellites have made up a huge space business. There are over 1,300 operating satellites in Earth orbit today, and thousands more in orbit that are out of commission. Space is a thriving business that accounts for over $350 billion annually in the world economy. Today we are in the midst of a revolution, replacing the huge, costly satellites of the past with small, nimble, new space satellites. I've been a space researcher for a long time. I've been part of many robotic missions to study the sun, the planets, and systems well beyond our solar neighborhood. I've worked with NASA, the National Oceanic and Atmospheric Administration, NOAA, the United States Air Force, and many international counterparts to plan and execute space programs. What's it like to pursue an idea and to see it come to fruition? When you're lucky enough to be involved in the planning of a new space mission, to go somewhere in space with new instrumental eyes, when you're really in for some fun when you do that, the most important moment in any researcher's life is when he or she says, "That's odd." When you see something puzzling that's not the way it's supposed to be, then you are really on your scientific way. Earlier, I mentioned the discovery of Earth's radiation belts by James Van Allen. I was privileged to be a student of Van Allen some years after his pioneering discoveries. In recent years, I've been further privileged to work on a modern NASA mission named after and dedicated to the memory of Dr. Van Allen. Let me illustrate how space missions are accomplished by walking you through the history of what is now called the Van Allen Probes mission of NASA. So what exactly did Van Allen and his co-workers discover back in the late 1950s? As shown in this diagram, they found that there are 2 distinct and separate belts of radiation around our planet. The inner belt or zone is filled with extremely energetic protons produced by galactic cosmic rays interacting with the Earth's upper atmosphere. In between, there's a dead zone called the slot region without many energetic particles. Then we find the outer belt made up of very energetic electrons. This was the view scientists held for some 50 years. During the decades following Van Allen's discoveries, we came to a much deeper understanding of our star, the sun, and how this highly variable star drives changes in Earth's space environment. Huge blasts of energy from the sun called coronal mass ejections can dramatically affect us on Earth. This animation shows how a 10 billion ton burst of material from the sun can move at maybe 7 or 8 million miles an hour and can severely distort the protective magnetic umbrella that surrounds our planet when it impacts. These solar storms are the key space weather concern we have as a modern technological society. In late October of 2003, the sun erupted with huge fury. It produced a whole series of fierce coronal mass ejections, and many spacecraft around the Earth were severely affected. The normally tranquil Van Allen belts were completely disrupted and distorted. The outer Van Allen belt electrons were transported into places they had never been seen before. These fascinating changes were reported in prestigious science journals like Nature magazine. Seeing such remarkable changes in the Van Allen belts in 2003 caused the entire space community to realize that a much deeper understanding of how the radiation belts are produced and altered by the sun was really needed. The U.S. National Academies of Sciences and Engineering strongly suggested in their decadal report of that time that a new mission called the Radiation Belt Storm Probes, or RBSP, be immediately undertaken. This sent NASA into mission development mode, and it put into motion actions by the Office of Management and Budget and ultimately Congress to approve this new mission. NASA and congressional approval quickly, by government standards at least, led to the establishment of a project office at NASA's Field Center, the Goddard Space Flight Center. The RBSP project, as it was called then, was established and worked with the quasi-governmental Applied Physics Laboratory in Laurel, Maryland, to design and develop a pair of large spacecraft that would fly in Earth orbit. This picture shows the spacecraft design that NASA and the Applied Physics Laboratory came up with. In 2006, there was an announcement of opportunity by NASA. This invited proposals for scientific instruments to fly on these RBSP spacecraft. Myself and other researchers and engineers in my institute, the Laboratory for Atmospheric and Space Physics, were very pleased to be chosen by NASA to build the approximately $20 million set of instruments to measure the highest energy particles in the Van Allen belts. After pre-selection activities, which took a fair amount of time, last began the design and development of the new RBSP instruments in 2008. The instruments were completed and integrated with the RBSP spacecraft themselves in early 2012. On August 30th, 2012, the twin RBSP spacecraft were ready to go. They were integrated into the nose cone of the United Launch Alliance Atlas V rocket at Cape Canaveral facility in Florida, and they were ready to launch. It was a beautiful nighttime, picture-perfect launch, and the two RBSP spacecraft were inserted into orbit. The expectation was that the satellites would largely confirm the basic understanding of the Van Allen belts that had built up over the past decades, and we would get a deeper insight into this pretty well-established story. The instruments from the University of Colorado and LASP were supposed to be turned on about 35 days after launch. I insisted as principal investigator that we get started on the science mission much sooner than had been planned. Instead of following the slower schedule, we turned on our amazing new instruments just 2.5 days after launch. What we found was that scientists had been wrong for over 50 years. Often there were really 3 Van Allen belts, not 2. This rocked the research world and the public. It led to tremendous public and scientific interest with publications in the most prestigious science journals such as Science and Nature. From the October storms of 2003 to the publication of the groundbreaking RBSP results, or Van Allen probe results, took almost 10 years. It led to a new National Academy plan that I chaired for our space community, and another set of big NASA missions are now in development. I must say it takes a long, long time to rewrite the textbooks. So this is the way that the space business has worked. Government, then industry, then academia have had to work together over years and sometimes decades to go from a good idea or a burning question to flying a space mission. Only after this process can science be done and can the observations be completed. Often the spacecraft developed could rightly be called Battlestar Galacticas, huge in size and huge in cost. Designing, building, testing, and launching these big missions has become so costly that the space program, both civilian and military, has been sinking under its own weight. The modern, fast-paced world has demanded better, and we've been moving from old space to new space in just the last few years. Being in space is very much a business. Spacecraft operating anywhere above the Earth's surface have definite goals. What goal may be? That goal may be to facilitate communication, search for Earth resources, help predict the weather, perform military reconnaissance, or myriad other functions. Whatever the objective, the general goal of space systems is to do the best possible job for the most reasonable overall cost. But what does reasonable mean when you're assessing costs? If you're a space organization, what is your value proposition? In other words, what makes your space business really competitive and successful? Well, there are some pretty obvious answers to that question. For government, the value proposition in space is pretty clear and is really pretty constrained. If you are a government space leader, you have fiduciary responsibility. In the government, you want to maximize the benefit to society, minimize the risk to taxpayer dollars, be as fair as possible to all the players, and avoid negative outcomes with politicians or with oversight bodies. Government organizations have a vested interest in carrying out the big missions in just the same way they always have. This tried and true way is widely viewed as minimizing political and technical risk. For a commercial space company, some goals are to increase market share, invent new, highly competitive technologies, develop new lines of business, and make the stockholders happy. For industry, the bottom line is, both literally and figuratively, to make more money from happy customers. So what about academia? In the university setting, abiding by the government model is not particularly rewarding or fulfilling. Big, expensive missions take too long. The typical government-managed program takes much longer than a student's educational career, and often there is little or no innovation in the government approach. With the modern commercial model of space programs, there can be innovation, but there often are very few on-ramps for students to really participate and learn. Students and academic researchers often can bring exciting new approaches to solving space-related problems, but working between industry and academia often can be very challenging. In light of all this, what's the value proposition for academic space? Well, the answer might include pushing back the frontiers of knowledge, satisfying innate curiosity, educating and training the next generation in the workforce, like all of you, and serving the public good. And oh yes, have fun doing all of this. Academia usually is not motivated by profit. Space programs in an academic environment often can be driven by speed, nimbleness, and innovation, with an overall willingness to take more risk. This, it strikes me, is what our space program of today should be all about. What do you think?